Hello, welcome to the first lesson in the first module of my new course on networking fundamentals. In this module, we'll be exploring how data flows through the internet. Crucial to that is understanding the various devices which are involved to make that possible. In this lesson, we'll be exploring these various devices and their related concepts. We'll be doing this in two parts. In this video, we'll unpack hosts, IP addresses, and networks, and in the next video, we'll explore these devices. And let's just jump right into it by defining our first term, host. Hosts are any device which sends or receives traffic. For example, your computer is a host, your laptop, your phone, your printer, your servers, those are all considered hosts. But we're also in the cloud days, which means there's many cloud resources that can also be considered as hosts. Cloud servers, for example. Moreover, we're also in the Internet of Things days, which means anything you have at your house that sends or receives traffic is also considered a host. That smart TV you stream to, those speakers that are all synchronized with each other, smart watches, your thermometer that you can control remotely, that refrigerator that reminds you when you're out of milk, all of those devices are sending and receiving traffic, and therefore can be considered as hosts. Why this is important is because all of these devices follow the same rules for how they communicate to the internet. Later in this module, we'll be looking at everything a host does when sending or receiving data from the internet. In doing so, we'll actually be explaining how all of these devices communicate with the internet. Hosts typically fall in one of two categories, clients or servers. Clients are the hosts that are initiating the request, and servers are the hosts that are responding to requests. For example, let's just say this is the web server for the website www.site.com. Well, when this computer over here is making a request to ask for the website site.com, it's initiating a request and therefore it is considered the client. When the web server site.com is providing the content for site.com, it's responding to the request, therefore it is considered the server. Keep in mind, however, the terms client and server are relative to a specific communication. Meaning, at some point, this web server is going to have to update its files from a file server or a database server. Well, for that, the web server has to make a request to the file server to ask for new files. In that communication, the web server is the client and the file server is the server. We can take it a step further. This file server at some point might need to run some sort of software update. Well, when it's making the request to the update server to download the new software, it's acting as the client, and when the update server is providing the updates back to the file server, it's acting as the server. So the terms client and server are specific to the communication that is occurring. Now we've been calling this a web server, but I want to clearly define what that is. A server is nothing more than a computer with software installed which knows how to respond to specific requests. This guy right here is really just a computer that has software installed that knows how to serve web pages. You can turn any device into a web server by simply installing the proper web server software. It's the same way with the file server and the update server we discussed a second ago. In the end, they are merely computers with software that knows how to provide files or provide updates. Each server you encounter is simply a computer responding to requests. So that wraps up our discussion on hosts. Next, we want to define IP addresses. IP addresses are the identity of each host, and every single host must have an IP address if it means to communicate on the internet. Just like you need a phone number in order to send or receive phone calls, or you need a mailing address in order to send and receive mail, you need an IP address in order to send or receive packets on a network. This is what the IP address is. It is the identity of every single host. Now, these IP addresses are actually going to be stamped on everything that each host sends. For example, when this client over here makes a web request to site.com, on this packet, which includes what web page it is asking for, the client is going to stamp the source and destination IP addresses. The source IP address is going to be the client's IP address, and the destination IP address is going to be the server's IP address. In the same way, when the server responds by providing the web page, it's also going to stamp the source and destination IP addresses for that communication. Here, the source IP address will be the server, and then the destination IP address will be the client. Everything sent on the internet is going to have this source and destination IP address. Now, an IP address itself is really just 32 bits. A bit is a 1 or a 0, which means every single IP address is really just a different combination of 32 ones and zeros. What we do is we take those 32 bits and break them up into 4 chunks, which we call octets, and we convert each of those octets into a decimal number. This is how we get to what we know of as an IP address. The smallest binary number you can get with 8 bits is 0, and the largest binary number you can get with 8 bits is 255. That's why every IP address you come across is going to be 4 instances of the numbers 0 through 255. Now in this module, we're not going to be exploring binary. We've already created some videos that discuss binary. If you're interested in learning about binary and how this conversion happens, please check out those videos. There'll be a link in the description. Either way, that is what an IP address is. Now, these IP addresses are typically assigned in some sort of hierarchy, so let me explain that. Imagine this is the Acme Corporation, and the Acme Corporation owns every IP address that starts with 10.anything. Well, maybe the Acme Corporation has 3 different offices, one in New York, one in London, and one in Tokyo. And each of those offices is going to have a subset of the Acme Corporation IP space. New York might have everything that starts with 10.20, London might have everything that starts with 10.30, and Tokyo might have everything that starts with 10.40. Moreover, the New York office might have a few different teams. For instance, they might have a sales team, an engineering team, and a marketing team. And each of those teams would have their own dedicated IP address space. The sales team could have everything that starts with 10.20.55. The engineering team would have everything that starts with 10.20.66, and marketing would have 10.20.77. The London and Tokyo offices probably have those same teams as well, but each of their IP address space is going to start with the prefix for that particular location. This allows the IP address to sort of pinpoint where a particular host exists. For example, if we had the IP address 10.30.55.127, that IP address is the identity of a host that sits in the Acme Corporation, in the London office, on the sales team. Now, this breaking up of IP addresses into their different hierarchies is done through a process known as subnetting. In this module, we're not going to be covering subnetting, but we've already created some videos discussing how subnetting works. If you're interested in learning subnetting, please check out those videos. There will be a link in the description. For us, we're going to continue with our exploration of network devices. All of the hosts that sit inside each of these teams at each of these offices exist in what is known as a network. A network is what actually does the transportation of traffic between hosts. In its simplest form, anytime you connect 2 hosts, you have a network. If you plug these hosts directly into each other, you have a network. Before networks, in order to move data from this computer to this computer, you would literally have to walk up to this computer, plug in a disk, download some files, then walk over to the other computer, plug in that same disk, and upload those files. Networking and networks are what automated that process. They allowed these computers to share data with each other automatically. Now, if we take a step back, a network is really just a logical grouping of hosts which require similar connectivity. So let me explain that. At your house, you probably have some sort of home Wi-Fi network. On that network, you've got your computer, your printer, laptops, phones, a bunch of different devices which all have similar connectivity profiles, meaning they just use the internet or check email or something along those lines. Well, down the street from you, there might be a coffee shop that provides Wi-Fi for its tenants. And that coffee shop is going to have various customers that have various mobile devices that are all connecting to the internet. Well, these devices all have similar connectivity profiles. They just need access to the internet. But since they're coming from a different location as these devices, they are grouped into 2 separate networks. Now, networks can also contain other networks. For example, you probably have a school not too far from where you live, and that school has its own network. But within that school are a bunch of classrooms, and it's very possible that inside each of those classrooms, all the hosts in each classroom are grouped up into their own network. Now, these networks within other networks are sometimes referred to as subnetworks or subnets, and this is a very common occurrence on the internet. In fact, that illustration we just did with the Acme Corporation, with the 3 offices and the 3 different teams in each of these offices, well, the office location is a subnet of the Acme Corporation IP space. And the specific teams are a subnet of the New York IP space. So you can have networks within networks within networks. Either way, all of these networks then connect to each other. For example, you might be sitting at your house and might want to do some sort of working from home and be able to access the office networks. Or possibly you're studying from a coffee shop and you might want to access school resources. Well, instead of having each of these networks connect directly to each other in every possible combination, instead, all of those networks are connected to a central resource. namely the internet. In fact, what we know of as the internet is simply a bunch of interconnected networks. That's all the internet is. It's just a bunch of company networks connected to a bunch of school networks connected to a bunch of customer networks. Of course, what handles those connections are often the internet service providers, or the ISPs, but that goes a little bit deeper than we want to get at this point. Either way, that wraps up our discussion on hosts, IP addresses, and networks. In part 2, we'll continue our discussion by unpacking repeaters, hubs, bridges, switches, and video are these last two devices, switches and routers. But we can't really understand those until we understand where we've come from, so we have to start there. In the last video, we unpacked the idea of a network. We identified that a network is created anytime you connect two computers to each other using a wire. One thing to understand about sending data across a wire is that it decays as it travels greater and greater distances. If the two computers you're connecting are in the same room, then you don't really have to worry about it. The decay will still occur, but the signal will still get through, and therefore connectivity between these hosts is still attained. If, however, these hosts span greater distances, maybe you're connecting two computers on opposite sides of a building, or even in two different buildings, then you might have a problem. If the signal decays before it gets to the other side, then these two hosts cannot share data. In those cases, what you need is a repeater. A repeater is a device whose sole purpose is to regenerate signals. Anything that comes in on one end simply gets regenerated out the other side. This allows you to connect devices together which span greater distances. So far, we've been talking about networking from the perspective of connecting one host directly to another host. Well, if you add a third host, you now have to connect that host to all the other hosts which you've already established. And if you add a fourth host, you now have to connect this fourth host to all the hosts that already exist. And again, if you add a fifth host, you now have to connect this fifth host to every host that has already been connected. As you can see, connecting hosts directly to each other simply doesn't scale. Instead, we created devices which we could put at the center of every network and connect all the hosts to those devices. And these devices would then handle funneling communication between these different hosts. The benefit to these types of devices is that if a sixth host gets spun up, it's very easy to simply connect it once to that device, and now it has connectivity to every host that has already existed. That's what all of these are. And the first of these types of device that we're going to discuss is known as a hub. A hub is nothing more than a multi-port repeater. Earlier, we discussed repeaters, and we said all they do is regenerate signals. Well, hubs do the same thing, except they do it across multiple ports. For example, if these two hosts over here need to communicate, when one of them sends a packet to the other, it'll hit the hub, and the hub will simply duplicate that packet and send it out all remaining ports. That'll allow what this guy sends to arrive over here. This fixes the scale problem. A hub is the first device that allows us to connect multiple devices in the center, and now all of them have connectivity to each other. But as you can probably see, the problem with a hub is that everybody receives everybody else's data. These two hosts over here, which are uninvolved in the communication between these two hosts, are receiving a copy of everything they send. Which brings us to bridges. Here, we have two sets of hosts, all interconnected using a hub. And a bridge is meant to sit in between hub-connected hosts. Bridges, by definition, only have two ports. One port facing one set of hub-connected devices and another port facing the other set of hub-connected devices. Bridges will also then learn which hosts are on which side of the bridge. This will allow the bridge to contain communication to only the side that is necessary. For example, if these hosts again need to speak to each other, when they send data to each other through that hub, the hub is of course going to simply regenerate that signal out all ports. And notice that the bridge is going to be getting a copy of that packet. But the bridge knows that the other green host is on this side of the bridge, and therefore the bridge isn't going to bring that packet to the other side. The bridge is the first type of device that helps contain packets only to their relative networks. On the other side, if these hosts need to speak to each other, they can also send packets to each other through their hub, and once again, the bridge will not let those packets bleed into the other side because it knows the yellow devices exist on the right hub. And of course, if this device needs to send something to this device, the bridge is going to know that that traffic is going to have to cross the bridge, and the bridge will allow that packet to traverse to the other side. The main takeaway is understanding that bridges can learn which hosts are connected on either side of the two ports of the bridge. Now this finally brings us to switches. Switches are sort of like a combination of hubs and bridges. They are like hubs in the sense that many devices can connect to the switch, and they are like bridges in the sense that they can learn which hosts are connected to each port. The main difference is that they're doing it on a per port basis, which means if these two hosts want to speak to each other, the switch will know that the only ports that need to receive this traffic are the two that are connected to those green hosts, and will keep that communication contained to just those ports. Moreover, if these two hosts want to speak to each other, the switch will again make sure that that communication only flows between the relative ports. So this is how a switch is like a combination of a hub and a bridge. The formal definition of a switch that we want to use is that a switch is a device which facilitates communication within a network. Earlier, we defined a network as a logical grouping of hosts which require similar connectivity, which means all of these devices over here all belong to the same network. Moreover, networks all share the same IP address space, which means this network owns all the IP addresses which start with 192.168.1.anything. And this host's identity is the IP address 192.168.1.33. And this host would be 192.168.1.66. And this set of devices could very easily represent all the different hosts on your home Wi-Fi network. Maybe this device is your printer, and this device is your laptop, and this device is your mobile phone, and so on. Or maybe this network and these devices represent all the PCs that might exist within a particular classroom of the school network. Or maybe, even further, all of these devices represent hosts that exist in the sales team of the London office of the Acme Corporation. One way or another, since all these devices are connected with a switch, they all belong to the same network. Now, let's go back to that example of the school network. We said that the school likely has many different classrooms, and each of those classrooms belong to their own network, which means this would be a more accurate representation of the school network. We would have classroom 2 owning that IP space and classroom 3 owning that IP space. Now, the reason you might want to separate these two sets of devices into their own network is because they might have different connectivity requirements. For example, maybe these computers over here all belong to the biology classroom, and all they need is simple internet connectivity. But maybe these computers over here belong to the computer science classroom, and they not only need internet connectivity, but also access to various cloud resources to do their studies. Well, since these computers have different connectivity requirements than these computers, it's a good idea to separate those out into separate networks. Now, in both cases, we can still use switches to facilitate all the communication within the networks, meaning this switch can handle all the communication between these three hosts, and this switch can handle all the communication between these three hosts. But what happens if this host down here wants to speak to this host on a different network? Well, if a switch can only facilitate communication within a network, we would need another type of device to handle the communication between networks. And that device would be a router. A router is a device whose primary purpose is to facilitate communication between networks. At the very least, you're going to need that router to connect you with the ultimate network of networks known as the Internet. So let's unpack this further. Routers provide traffic control points between networks. Let's say we wanted to limit the traffic that could go from this PC to this PC. Well, since these two PCs aren't separate networks, all that traffic has to flow through the router, creating a great place to add security policies or traffic filtering, or even redirecting that traffic elsewhere entirely. Since routers sit on the boundary between networks, they provide a logical location to apply security policies. This type of security filtering isn't traditionally available on switches. These days, there are modern switches that can do such filtering, but it is generally accepted that the devices sitting on the same network don't typically need filtering for traffic traveling within the network. If you had devices that needed different types of connectivity, you'd want to place them in different networks. The network boundary is what is meant to be the logical separation of devices. The way routers work is that they learn which networks that they are attached to, meaning this router is going to learn that on this interface it's connected to the 172.16.20 network, and on this interface it's connected to the 172.16.30 network, and out here is the direction to go to the internet. The knowledge of each of these different networks is known as a route, and all these routes are stored in what the router calls a routing table. A routing table is therefore all the networks that a router knows about, and the router is going to use this routing table in order to funnel traffic out the appropriate interface. Now, when we say a router learns which networks they are attached to, what we mean is that a router has an IP address in every network that they are attached to. For example, when this router is attached to this network, it is given an IP address in that network. This interface's identity is the IP address 172.16.20.1, and this interface's identity is the IP address 172.16.30.254. This IP address is going to serve as what's known as a gateway. A gateway is a host's way out of their local network. For example, this host over here has the IP address 172.16.20.33. But if that host wants to speak to something on a different network, it knows it's going to have to go through a router. And the IP address of that router is stored as that host's default gateway. Notice this host has a default gateway of 172.16.20.1. That's this interface IP address of that router. Now, if we go a step higher than that, routers are actually what create the hierarchy in networks and IP addresses that we discussed in the prior sections of this lesson. For example, the New York office of the Acme Corporation that had all the different teams that each had their own IP networks, well, each of those networks are connected to different routers, and each of those routers are then connected to another router. And if a host in the sales team wants to speak to a host on the marketing team, it's going to use its gateway, which is its closest router IP address, which is then going to send the packet to the next router, and then finally to the host on the marketing team. The Tokyo office of the Acme Corporation is likely going to have a similar setup, and both of these routers are then likely going to connect to the internet. The internet is nothing more than a bunch of different routers itself, meaning if a host on the marketing team wants to speak to a host on the engineering team in Tokyo, that host will send the data to the router, which will send the data to the next router, which will send it through all the routers on the internet, which will finally send it to the Tokyo router, and finally to the engineering team. And that is how data is going to flow across the internet. And that is the role that routers play in making that possible. Now, the last idea I want to leave you with actually involves pulling back the definition of switches as well. There's something important you have to understand about what we've defined as routers and switches. Routing is the process of moving data between networks. A router, as we have described it, is simply a device whose primary purpose is to perform routing. In the same way, switching is the process of moving data within networks. And a switch, as we have described it, is a device whose primary purpose is switching. The reason I bring that up is there are many other types of network devices that exist out there. Access points, firewalls, load balancers, layer 3 switches, proxies, and there's even devices that only exist in the cloud, like virtual switches and virtual routers. One way or another, all of these devices are going to perform routing or switching or both. So later on in this module, when we describe what a router does or what a switch does, what we are actually describing is what any device does that implements routing or any device does that implements switching. And with that, we close our lesson on network devices. In part 1 of this lesson, we unpacked hosts, IP addresses, and networks. And in part 2, we continued that discussion by illustrating repeaters, hubs, bridges, switches, and routers. In the next lesson, we're going to give you a practical perspective on the OSI model. This will lay the foundation to understand what all of these devices do to enable data flowing through the internet.